Okay, so let's kind of go over that lab mini assignment, whatever, from Friday, because there's a lot of this is going to be on the test tomorrow, okay? So I want to make sure everybody's cool with what's going on. So, that problem number 4, and here's going to be the basic idea, is that you're going to throw this ball up in the air, and you've got to break it up into 2 distinct parts, okay? So your total flight time is 4.3. So, and I promise you, you're going to have a problem like this on the test tomorrow. You mark my words, okay? I'm going to ask you, like, what's the launch velocity? What's the velocity of it lands? Something like that, okay? You have to remember that this flight has 2 distinct parts. What's on its way up and what's on its way down, okay? So the 4.4 seconds is the entire time. So that means you're going to spend 2.20 seconds going up and 2.20 seconds going down. And you can assume that as long as this thing is symmetrical, okay? And that's the whole key to this. So if it's symmetrical, listen very carefully to the terminology. The launch velocity and return velocity are going to be the exact same numeric value, but they're going to be opposite signs, okay? The speed, which is just how fast it's going, is going to be the same. So speed is the same, velocities are the same numeric value, opposite signs. So if it's going to launch at 21, it's going to land at negative 21. But the speed's going to be 21 and 21, okay? But you assume that this flight is symmetrical. So your velocity time graph is going to look something like this. And your position time graph is going to look something like this. Okay? Very crude, but that's what it's going to look like. So, on 4A, you want to calculate the initial velocity of the ball when it's launched. If this is wrong, everything is going to be wrong. Okay? So, what I would recommend is you start with V equaling V naught plus AT. The whole key to this is to realize once that ball reaches its maximum height, Nick, what's the velocity of the ball going to be when it reaches its maximum height? 0. And how long is that going to take?
The moment it's there.
But how, in this situation, the entire time is 4.4. So how long is it going to take to reach that maximum height? 2.2. So at this point, if you do the V naught dat, okay, my final velocity is going to be 0. My initial velocity is what I don't know. Don't care about distance, not part of the story at this point. My acceleration is negative 9.8 meters per second squared. I know my time is 2.20 seconds. Now, let's just think this through. Is the launch velocity going to be bigger or smaller than 9.8 meters per second? Bigger. Why? Let me ask you this, literally this. Your acceleration is negative 9.8 meters per second squared, right? No, you're making this complicated. You're making this complicated. Don't make this complicated. Okay? What if the initial velocity was 9.8 meters per second? How long would it take to go to 0? What'd you say? If my initial velocity was just 9.8 meters per second, how long would it take to go to 0? Exactly 1 second, right? Okay? You have to understand what acceleration means. This acceleration is the rate at which your velocity changes. So if you start at 9.8 meters per second, it's going to take you exactly 1 second to go to 0. So since it took more than 1 second to reach its maximum height, I know my launch velocity has to be bigger than 9.8 meters per second. Okay? That's what I want you to think through. Okay? So, if you come in here and you solve this equation for V naught, you got V minus AT equaling V naught. Cool, right? do that and then plug in the numbers. Oh, I'm going to have 0 minus negative 9.8 meters per second squared times 2.20 seconds equals V naught. So look what happens in terms of signs. I have 0 minus a negative value. I'm going to get a positive initial velocity. That's what I know has to happen. So if you do this and you get a negative velocity, oh, something's wrong, okay? You're not going to launch this thing up in the air by shooting the ball down, okay? And if you get a negative number, don't go, oh, I'll just ignore it. It's okay. Okay. What's a negative sign between friends? Okay? No, you have done something wrong. If you get a negative time and you go, oh, man, something's wrong, just don't ignore it. Okay? You have done something wrong. All right? Okay. So that answer on 4A should be around 21 meters per second. Because if that's wrong, everything is wrong. Now, when you find that maximum height, there's a whole bunch of different ways you can find the maximum height. You could go to your velocity time graph and you go, wow, that's 21.6 meters per second. I know my height, I know my base is 2.2 seconds, I can find the area underneath that triangle. That's cool. It's like, oh, I like triangles. Good for you. Okay? You could use that equation. You know your final velocity, you know your initial velocity, you know your acceleration. You could do that. You could use distance equals 1/2 AT squared plus V naught time. Plug in 2.2 seconds, your acceleration of negative 9.8 meters per second squared, and your initial velocity of 21.6 meters per second. There's 3 different ways you can find the maximum height. I don't care. Okay? Pick the one that makes the most sense to you. Mathematically, the area of the triangle is the easiest. Oh, 1/2 base times height. 2.2, half of that, 1.1, 1.1 times 21.6, boom, there you go. That's the easiest mathematically. The other 2 are fairly complicated because you have to square values, but if you like that, hey, go with it. Now, on 4C, what's the final velocity of the ball? Okay, do not make this difficult. Okay? Look at it this way. You go, oh, V equals V naught plus AT. On the way down, okay, what's your initial velocity going to be? 0. You know your acceleration? Plug in 2.20 seconds because that's how long it's going to take for it to fall. You should get an answer on 4C that is the negative of your answer to 4A. Okay? And you can do that as long as everything is symmetrical. So, when you get to D, what I'm asking for on that one, the position time graph is going to look something like this. Now, here's the magic code. Okay? Here's the magic code. And I'm going to ask you a question like this on the test. It's going to probably be up to 30 days. I'm going to say, hey, what's the slope of a position time graph at a particular point in time? Okay? The magic code is that when I say, what's the slope of that position time graph at a particular instant in time, what am I asking you to find? Instantaneous velocity. So I'm not asking you to find the height, okay? I'm asking you, what's the slope of the line, which is the magic code for what's the velocity? How fast is this thing going? So at time 0, if you were to come in here and you were to draw that tangent line, oh, it's going 21.6 meters per second. There's nothing to calculate. You know how fast it's going at time 0. Now, at 1 second, okay, think this through. You started at 21.6 meters per second. This line is going to come down like this, okay? You're going to go over 1 second. Over 1 second. How far down are you going to go? 9.8. 9.8. All you have to do is take 21.6 and subtract 9.8. That's the short version, okay? And that, even though it's the short version, that actually shows a deeper understanding of what acceleration means. Okay, right, 21.6. 1 second. I'm either going to be going 9.8 meters per second faster or 9.8 meters per second slower. Okay, that's it. And you go, wow, I'm slowing down. I'll subtract 9.8. Easy peasy, lemon squeezy. There you go. So, now, if you're going, oh, but Mr. Burkamp, they call me Eddie Equation. I am the equation master. Okay, fine. So V equals V naught plus AT. You know your initial velocity is 21.6. 21.6 meters per second plus negative 9.8 meters per second squared. Plug in 1 second. You still take 21.6 and you subtract 9.8. You just use the formula to do it. Okay? And then at 2.2, the only thing that changes is that you put in 2.2 instead of 1. So all you have to do is just plug numbers in. So again, so on the test, and you mark my words, okay? Bubba is going to be throwing a roll of toilet paper in the air. It's going to be the problem. I'm going to say, what's the slope of the position time graph at a particular instant in time? I'm asking you to find the velocity of the roll of toilet paper. Okay? I'm going to tell you straight up. It's going to be Bubba and the toilet paper. Sit. Okay? I'm asking you to find the velocity. Okay? Anyway. Whatever you do on questions 5 and 6, do not use the word backwards, reverse, nothing like that. Okay? So your answers to 5 and 6 has nothing to do with going backwards. That has nothing to do with going in reverse. Okay? You can't tell that negative velocity means that you're going backwards and positive velocity means that you're going forward. Okay? So 5 and 6 say nothing about going backwards, forwards, to the reference point. You can't tell any of that. Okay? Fundamentally, ask yourself, is it speeding up? Is it slowing down? That's how you want to approach 5 and 6. What do you know about the signs of velocity and acceleration if something's speeding up? What do you know about the signs if they're slowing down? Okay? Are you erasing madly? Nope. I'm not erasing, and you can't prove it, Mr. Brookhaven. I'm wording.
Wait, you just said speeding up and slowing down. That's fine if we say that in
Yeah,
there?
that's fine. But I'm
Okay.
saying, don't tell me
Okay,
backwards
I
and
didn't say anything
forwards.
about that. I kept that one simple.
Yeah, just
Yeah,
don't
why do you
tell me,
make your
oh, it's going
questions too
backwards or
simple? They
something
make
like
you
that.
like
Or it's
question
changed
myself.
direction.
Okay, good.
Yeah. Okay, now let's talk about number 8. Okay? So in number 8, here's your setup. You have 2 different spaceships, okay? Enterprise and Columbia. They're at the same point in time. Okay, it's like some point in time in space, they're at the exact same location. They're going to go out, and they're going to come back. This one's going to go out, and it's going to come back. So one's traveling at, Enterprise is traveling at 450 meters per second, and the Columbia is moving at 600 meters per second. Okay? Are they going to change direction?
Yeah.
Yes.
So what does their velocity have to go to?
0.
Are they both going to accelerate?
Yes.
Because if they don't accelerate, guess what?
They're not
They're not going to change
changing.
direction. It's going to keep going forward. Okay? So they're both going to accelerate. Do both of their velocities have to go to 0? Yeah, because otherwise they can't change direction.
Yeah.
Are their velocities going to change sign?
Yeah.
Yeah, because they're going to change the direction. So here's what you know. You know their velocities have to go to 0. You know their velocities have to change sign. Okay? So if they have positive velocities when they take off, what's going to be the sign of their velocities when they get back?
Negative.
Okay? The total time is 86 seconds. So if it takes 86 seconds to go out and come back, how long is it going to take for that velocity to go to 0?
43 seconds.
Half the time. 40. You have to assume that it's symmetrical, right? So basically they're going to start here. 43 seconds later, their velocity is going to be to 0. 43 seconds later, it's going to be back to here. Okay? So on your velocity time graph, okay, you're going to have, this pen has been stupid today. Basically, you're going to have 2 lines that goes something like this. Okay? There you go. That's what it's going to look like. And how long is that going to take to get to that point where that velocity goes to 0? 43 seconds. So if all goes well on number 8, both of those accelerations are going to be somewhere between like -10 and -15. Okay? Somewhere between -10 and -15. Okay, now let's talk about number 9. I promise you, you what?
Nothing. If you're gonna say that's on the test.
Oh, I promise you, number 9. It's going to be the second to the last problem on the test. I'll even tell you where it's going to be on the test. Okay? It's going to be the second to the last problem on the test. Okay? It's going to be an entire page problem. Okay?
Entire page?
Entire page. That problem is going to
Oh,
be
I
one.
guess.
How many pages is the test?
1.
4 or 5. But that's like front to back.
Is there multiple choice?
It's
on
not
it?
Wait, how
front and
many
back?
sheets of paper?
Wait.
Oh, sheets of paper like 3.
Oh, okay.
Huh?
Well, so we
Yeah. Something
we
like
know what one page is gonna be.
that. Oh yeah, that's going to be one page.
So I went out of whatever.
Okay. So here's the setup. So here's the rocket. Okay? That looks surprisingly like a syringe. Okay? So here's your rocket. What's the initial velocity of the rocket going to be? 0. Okay? It's going to start at 0 meters per second. Now, you're going to fire the engines. What's the whole purpose of firing the engines? To create a positive acceleration or a negative acceleration?
Positive.
Positive. Okay? Rocket engines that don't produce positive accelerations don't sell very well. Okay? It's like, what does your rocket do? It goes down in the ground. Cool. Sign me up. Okay? No. Huh? Okay, well, if you could. So, here's the rocket. You're going to create a positive acceleration. So your velocity, you want your velocity vectors to get bigger and bigger and bigger pointing upwards, right? That's the whole point. Okay? It's an acceleration machine. So you want an acceleration vector pointing upward. That's what you want to have happen, right? It's the whole purpose of the rocket engine. So what's happening is that you're going to reach a velocity 30 meters per second, so you know your final velocity. You know your initial velocity is 0, and you have a height of 25 meters. So what did I not give you on problem number 9? Oh, beyond that. I didn't give you the acceleration vector. I didn't give you time. Okay? So what's the one thing the equation you can use when you don't have time? That equation, right? You know the initial velocity, you know your final velocity, you know distance. What sign should your acceleration be? Positive or negative?
Positive.
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 So on number 9A, that acceleration should basically be your age.
Yeah.
Okay?
Not that. Very close.
I'm not 100. I'm just kidding. I'm just kidding. I'm joking. I didn't get 100 something.
Oh, thank God. Because if you did, it's like,
Nah, I'm messing.
Okay. Now, the next thing you want to do is find the time. So, by the way, without giving it away, your acceleration should be 18 meters per second squared. Okay, that's what you should get as 9A. Okay? Fantastic. Now, you want to figure out how long it's going to take. Now think this through. Your acceleration is 18 meters per second squared. You're going to go from 0 to 30 meters per second. If you start at 0, at the end of 1 second, how fast are you going? 18 meters per second. At the end of 2 seconds, you're going 36. Is your velocity bigger or smaller than 36?
Smaller.
Smaller. So guess what? Your time should be
Between 1 and 2.
between 1 and 2 seconds. Okay? Think through what that acceleration means. So your answer for that time, oddly enough, should be between 1 and 2 seconds. Okay? I'm just telling you. And pay attention to the significant digits. I gave you 3 significant digits in every one of these answers. Okay?
Yes.
Now, at this point, we fired this thing for 2 engines, or for about 2 seconds, okay? It's going about 30 meters per second, 25 meters above the ground. 25 meters above the ground would be about 10 times the height of this seat, okay? Now, at that point, that's like me throwing this syringe up in the air, okay? I let go of the syringe. It's going 30 meters per second. As soon as I let go of that syringe, what's the only force acting on the syringe or the rocket, or whatever you want? Gravity. What's the acceleration caused by gravity? Negative 9.8 meters per second squared. There is nothing to calculate for that value. Okay, where I ask you, when I shut off the rocket engines, what's the acceleration? There's nothing to calculate. Just put negative 9.8 meters per second squared. Because that's the only force acting on this. Now, here's what you want to visualize. Okay? On your velocity time graph, you went from 0 to 30 meters per second.
Yep.
Okay? And that took about 1.6 seconds. Okay, that's an ish, but it's about 1.6 seconds. Okay? Now, what does the slope of a velocity time graph give you? Watch out for that fire extinguisher. I know, that's why I said that. I didn't what you did.
I want to know, packet-wise, if you happen to have one more, and I might have to print you another, because you already out.
Yes.
Okay.
Oh my god, that's a big bag
Do
of
you have
goldfish.
everybody?
Yeah.
Is it? Can I have some?
Can I have some?
Ella didn't eat any of mine
Okay.
because she was just.
I have a lot of socks.
Okay, yeah, I thought,
Maybe you have a couple.
huh,
Okay.
okay,
Where is it?
okay. What is it?
That's pumpkin bread.
Oh, brownies?
No, it's pumpkin bread.
Oh, tomorrow's test day, I'm just saying.
My dog.
Oh, really?
No, they actually do eat all of the desserts. I'm not
What kind of
lying
dog
to
is
you.
it?
A smart one who can get on the counter.
A smart dog.
A sport dog?
He can open doors too. I hate dogs.
That's because it's so fresh to me. Okay. Anyway, back to our story. So, here's the deal. So, you fired the engines, you shut it off. The slope of a velocity time graph gives you acceleration. So, and this is going to tie into the next Deuteronomic forces, okay? So at this point, I shut off the engines, right? Even though it's going up in the air, what's it doing? Speeding up or slowing down? It's slowing down, okay? So at this point, I shut off the engines. That's at this peak right here. I shut off the engines. So immediately, what's this graph going to start to do?
It's
Go.
going to slope down.
Doink, okay? Now, here's what you're tempted to do. You're tempted to confuse this with the position time graph and go, oh, it's going to go something like this, okay? Like a parabolic curve. This is not a position time graph. This is a velocity time graph, okay? On a velocity time graph, listen to me. You only draw straight sloping lines. If you find yourself drawing like curved lines, stop. Okay? You have done something wrong. Alright? You are never going to draw a curved line on a velocity time graph. You're only good. Now, they might change slopes, you might change like the slope of it, but within each individual segment, you're only drawing straight sloping lines. So at this point, now your acceleration becomes negative 9.8 meters per second squared. So you had an acceleration of 18 meters per second squared, and then it becomes an acceleration of negative 9.8. Now, listen to me. You keep a running clock. So when you find that time for it to reach its maximum height and that velocity goes to 0, you have to take that initial time and add to that the time that it takes to go from 30 to 0, okay? You keep a running clock. So here's the time when the engines were fired. then you add to that the time it takes to go from 30 to 0, okay? Keep a running clock. If you hand in the test tomorrow and you haven't drawn a graph like that, you have done something wrong, okay? Seriously, if you haven't drawn like a roof or a triangle, whatever you want to think of it, if you haven't drawn something like that tomorrow, when you hand in that test, you have done something wrong. And if you draw that as like an igloo, oh, it's an igloo, it's going up and the rock is, no, okay? No, it's going to go 2 distinct lines like that, okay? Got that one? Cool. Promise you, second to the last problem on the test, okay? What? Does that stress you out when I tell you where it's going to be, or do you want it to be a
I
surprise?
just don't want it to be on the test.
Okay, well, I'll take it off.
All right, good.
No. Okay.
I just don't even want to test.
Well, I'm sorry. It's
Good
kind
thing
of
I'm not
nice.
taking it tomorrow.
All right. I look at it as a celebration of learning. That's how I see it. That's how I feel.
That's great.
Okay, now let's talk about the lab. So you bounced the ball, you had this, oh, you went doink, doink, okay? So you type it start to finish, okay? So, Topher, what was your total time
Wait,
on the lab? Total time,
1.51 seconds.
1.51 seconds. And what was the maximum height?
2.03.
2 point what?
03.
Meters?
Yeah.
Okay. So what you're trying to find is the initial velocity going up, right? So what I would recommend, there's 2 options that you can do. Just, you know this is what your velocity time graph is going to look like, okay? You're trying to find the velocity of that ball when it bounces off the floor. So if I'm Topher, I'm going to sit there and go, well, I know that area is 2.03 meters because that's how high the ball bounced. So I know the area underneath that triangle. If I take that time and divide that by 2, I'm going to know the base of the triangle. It's cool. And I know the area of a triangle is 1/2 base times height. Okay? I know my area because I know how high the ball went. I know my base because I know half the time. And I'm trying to find the height. Okay? That's an option. So if you like triangles and area, that's cool. You go, Mr. Burkamp, I like formulas. Okay, fine. You know how high it went up? You know what 1/2 is. Hopefully nobody struggles with that. You know the final velocity is going to be 0. You know that's going to be half your time. You do the exact same math, you change the sequence. Okay? It's the exact same idea. Now, if I were to guess, just pulling out a number, I'm guessing your initial velocity was somewhere around 7-ish meters per second, Topher?
Initial?
Yeah.
We had under that.
But it was something around there.
Yeah.
Okay? All right? So, once he gets that, then he can find his acceleration using A equals V minus V naught over time. Because remember, all you're trying to find here is the slope of that velocity time graph. Okay? You know, your initial velocity is some positive number. Your final velocity is 0. Divided by time, boom, there's your acceleration. Okay? And then you're going to do the same thing on the way down. Now, I'm going to tell you this straight up. I've got all these labs to grade. The only thing that I can grade is your procedure. That's all I can grade. Okay? That's all. That's the only thing I can look at. So make sure that I see exactly what you're doing. Okay? And so help me. If I get something, let's say Topher would do this, but let's say Topher writes down 2.03 divided by 0.81, whatever, gets me a number. Okay? I will flip out. Okay? Because I have no idea what that means. Great. You wrote down numbers. 10 out of 10, Skippy. No. Okay? Show me your work. And the only time in the mini lab that you're going to use that negative 9.8 meters per second squared is when you're calculating that experimental error. So on that experimental error, you're gonna take whatever you have, whatever your calculated acceleration is, okay, like negative whatever that is, minus a negative 9.8 meters per second squared, divided by negative 9.8 meters per second squared, times 100. So on the mini lab, that's the only time you're gonna use negative 9.8. Okay, that's the only time. And make sure, for the love of physics, that I can see exactly what you have done in all of those calculations. Okay? All right. Anything else you want me to go over on this? If you want to hold on to this and use it to study and hand it in tomorrow, that's cool. If you're done with it and you feel good about it, you can hand it in. Okay? So whatever you want to do. But I promise you, you make sure that you completely understand questions 9 and 10. Okay? I promise you, there's going to be one like 9 and 10 on the test.
No.
I'm ready to not take it tomorrow.
Huh?
I'm ready to not take it tomorrow.
Okay, so this problem that I gave you, there's a little slip of paper. Mark my words, this problem is going to be the last problem on the test, okay? The only thing I'm going to do is change the numbers. So what we're going to do is we're going to make sure everybody knows that I'm going to give you like 10 minutes, and I want you to work this problem. So here's the setup. So here's this building, you're standing on top of this building, and you're going to throw a ball up in the air with an initial velocity of 12 meters per second. So the ball is going to go up, and then the ball is going to fall all the way down to the ground. Okay, so this is not symmetrical. Okay, the ball is going to fall much further on the way down than it went on the way up. Okay, so your initial velocity is 12 meters per second. The building itself is 8 meters tall. Okay, and again, to give you some perspective, this ceiling is about 2.5. So this height is about 3 times taller than this room is. Okay, so it isn't like, hey, we're on top of the Empire State Building. No, it's a fairly decent height building. Okay, so ball's going to go up. Ball's going to fall all the way down like this. Right? That's going to be your setup. So here's what I want you to do. I want you to pretend like this is the last problem on the test. That's what it's going to be tomorrow. So there's a whole bunch of things that you need to find. Okay? Like for example, you need to find the time up. You need to find the time, and you don't have to work them in this sequence. You need to find the time down. You need to find the maximum height. You need to find the velocity at impact. And you need to find the time total. And then we need to draw a position time graph and a velocity time graph. Okay? So here's what I want you to do. And you don't have to work this in any particular sequence, okay? But here's what I want. If you get a portion of this problem done, okay, I want you to come up here. I want you to write down 3 things. I want the solved equation. Okay, I don't have to see the equation that you start with. But I want the solved equation. Time, height, velocity, whatever. Then I want the numbers substituted in, paying attention to the signs of velocity, acceleration, displacement. And then I want the answer. Okay? So if you say, Mr. Burkamp, I know I feel good about finding that time up. So here's what I want you to do. Come up. I want the solved equation. Then I want the numbers. Then I want the answer. Okay? So I'm going to give you about, and by the way, there is like probably 10 different ways you can solve this problem. Okay? There's a whole bunch of different ways you can find the velocity to impact, time down. There's literally 10 different ways you can solve this problem. So if somebody else works it a different way, but you still came up with the same answer, hey, don't sweat it, it's okay. Now, if you worked it a different way, you got a completely different answer, ooh, that's gonna be problematic, okay? So, I'm gonna quit talking, I'm gonna give you all about 10 minutes to work the problem. So, stop you on the camera.
Record.
No, you don't have to.
Nope, it's fine. Well, actually, yeah, you need something to record.
Okay, so I'm purposely going to roll Jack underneath the bus, okay? So let's start with the things that are right. So let's start with the time up, okay? So on the test, this is, I'm going to tell you straight up, this is the level of work that I'm going to expect to see. I want to see the calculations, and I'm going to check that you are consistently using negative 9.8 meters per second squared. I want to see those signs. That's part of the points for this process, okay? It isn't just getting an answer. It's can I track what you're doing, okay? Because this is like your culminating thing, right? So this is what I expect to see. I want to see the solved equation. I want to see the numbers, and this is where this is cool. I've got 0 minus 12. This is going to give me a negative number. Divided by negative 9.8 meters per second squared, I get a positive time of 1.22 seconds, okay? Now, why does it make sense that before I did any calculations, how did I know my time up was going to be more than 1 second?
Because of the velocity.
Wow.
Oh.
Because your velocity exceeds 9.8 meters per second. which is
Fantastic.
gravity.
My velocity was a little bit more than 9.8 meters per second, so I got to figure my time up is going to be more than 1 second. Seems reasonable. So before you even start down that road, ask yourself, wow, is my time up going to be more or less than 1 second? Start with that idea. Now, there's only really one way you can find that time up, okay? It's kind of a one-trick pony. That's it. Now, let's talk about the time, or that maximum height. So I'm going to move down here to this one, okay? Now, this is where this one's cool. So, we've got v equals v squared minus v naught squared over 2a. Notice what happened here. I've got 0 squared minus 12 squared. Okay, this isn't negative 12 squared, it's 0 minus 12 squared. So that gives me a negative number on top. I got a negative number down here, and this is what I'm going to look for, okay? And then I've got 7.35, correct number of significant digits. I'm going to add that to 8.00. This is to the hundredths, that's to the hundredths. That's why that ends up at 15.35, okay? That's one way that you can find the maximum height. If it were me, this is how I would have done it, okay? Because this is going off of known values, okay? So that way, hey, these are the numbers Burkamp gave me. I'm going to run with these. Now, here's the other way that you can find the maximum height. Your velocity time graph is going to look something like this, where you have 12 meters per second, and we figured out that that was 1.22 seconds. So if you wanted to, you could use the velocity time graph, and you could find the area underneath them. It's like, Burkamp, I'm like triangles. Fine, use your velocity time graph. But here's the only potential glitch, is that if that time is wrong, then that maximum height is going to be wrong, okay? That's the only potential thing that could go wrong. Either way, you're going to get the same answer, okay? Now, time down. There's 2 different ways you can do the time down. So here's what Jack did, okay? And I want to pick on Jack, and I purposely said, Jack, you write this straight up like you have it. So if you're going to do this, and Jack started with the right equation. He started off fine. But he let that V naught drop out too early. Yes, that V naught is 0, but you don't drop that out until after you get it solved, okay? So if he's going to find time, what he needs to do is write that as V minus V naught over A equals time. Now, here's the deal. On the way down, what's your initial velocity? 0. So you have to visualize this as two completely separate situations. One where you went from 0 to 12, and you're at the maximum height, and then it's just like you're starting over. I'm starting over, and I'm going to drop this ball, and I'm going to let it fall, and I know it's going to land with a velocity of negative 17.3. Okay? That's it. So then you're going to go, oh, my final velocity is negative 17.3 meters per second minus 0 divided by negative 9.8 meters per second squared, and that's going to get you time. Because if Jack had done this on the test, here would have been my thoughts. It was like, okay, let me get this straight. I have failed Jack as a physics teacher. Okay? Because first off, Jack put down a positive velocity, which means that the ball was going up when it lands. Small problem there. Then, Jack's going to take a positive velocity divided by a negative acceleration and then somehow magically come up with positive time. And at this point, I'm going to feel like an absolute failure as a physics teacher. It's like, I have not taught Jack anything. Okay? Other than plug numbers into a calculator, and I have failed him. Okay? So, but this is what you want to work this problem like in a holistic standpoint. Okay? This isn't just getting numbers. At this point, Jack should realize, like, whoa, this is bad. I'm going to have negative time. This is not going to end well, okay? But again, this is, so I would not give Jack full credit for this. Mathematically, Jack got the right time. Conceptually, Jack screwed it all up, okay? But I guarantee you, this is what happens most of the time. This is why I sacrificed Jack, okay? Because I guarantee you, he's not the only one that did that, right? But that's what I want you to look at. Now, if it were me, I wouldn't have solved it like Jack did, okay? And here's the reason why. Jack based that off of velocity, and that velocity was based off the maximum height. So Jack is using a number that was like 2 steps away from the information that I gave him, okay? What I would have done, you're going to get the same answer. What I would have done personally, I would have used distance equals 1/2 AT squared plus V naught time. And I would have said, okay, on the way down, my initial velocity is 0. It's going to fall. I know that it's going to fall that negative 15.35 meters. Okay, so I can solve this and go 2D over A. The square root of that is going to equal time. Okay, so I would have done this. Okay, mainly because how Jack did it and it works. Okay, but the problem is that he used a height, and the height was used to find the velocity. So if either of those 2 previous calculations were wrong, that calculation of time now becomes wrong. Okay, so I like this one because of the fact that I'm just going off of, oh, here's how high it is, this is how far it's going to fall. Okay, whatever works. You just have to find the way that works best for you. Okay, then the velocity of impact, where was that one? Now, this is what's really nice here, okay? So Morella used that equation, as you can. It's wonderful, okay? So this is what's nice. She had a negative 9.8 meters per second squared here. She had a negative displacement underneath that radical. That was cool. Now, what was most impressive is that she chose the negative root, because your calculator is just going to tell you the velocity is 17.3. You have to realize, oh, the square root of 4 is plus or minus 2. So she just had to realize, oh, I've got to pick the negative root coming out of that answer. Okay? So the disadvantage of this is that you have to remember to choose the negative root. The other way that you could have found the velocity at impact, and it's equally valid, you could have used V equals V naught plus AT. So if we use Jack's time of 1.77, you could have said, oh, on the way down, that starts at 0 meters per second. I've got an acceleration of negative 9.8 meters per second squared. I get a time of 1.77 seconds, or whatever you got for that time down. The beauty of this one is that it automatically generates a negative value for the velocity. The disadvantage is that if you screwed up the time, then you're going to screw up that velocity. Okay? Got that? So here's what's going to happen. Here's going to be the last two problems on the test. Okay? Each one is going to be a page long. The second to last problem is going to be the rocket problem. Start at 0, it's going to fire up. You're going to go a certain velocity. You're going to go from that velocity to 0. You're going to draw up a velocity time graph. Okay? This is going to be the last problem on the test. Literally, the only thing that I can do on this problem is change the numbers. Okay? That's it. I can change the numbers. So what I would recommend, because you know this is going to be the last problem on the test. You know this is going to be the last problem. When you get this test, like, wow, boom, here it is. Okay? Ball off the building. Will you work this problem again and again and again? And you change the numbers. And then you work that problem again and again and again. And you think, wow, are there different ways that I can solve this problem and still get the same answer? What if I use the velocity equations? What if I use that equation? That's what you want to think through. You know what the last two problems on this test are going to be. Okay? So don't get there, give it to you, and it's like, oh man, Burkham didn't tell us that was going to happen. Ah, he's such a jerk. Okay? I wrote the test. It isn't like I walk in tomorrow morning and it's like, oh man, I didn't teach him how to do those problems. Oh, all right, sorry kids. No, okay? I write the test. When I tell you what's going to be on the test, I'm not kidding. Okay? So, what last thing I'm going to give you is here's a list of things that you need to know for the test. Okay? And then I'm going to give you a set of review problems for the test. Okay? A blank one. And then I'm going to give you the answer key to it. Okay? If you do nothing else, you work problem number 8. So problem number 8 is a rock thrown off a bridge problem. If you do nothing else, you work number 8. Also, be able to think through different situations. What happens when something is speeding up? What happens when something's slowing down? Okay? Be able to think that through in terms of what are your velocity vectors doing? What's that going to look like on a position time graph? What's that going to look like on a velocity time graph? Okay? All right, I'm done. Stop you on the camera.